All right, so example number one, we've got r equals 4 minus 4 cosine theta. We got through this one in each of our 3 classes today. Somehow I forgot to start the video, so again, I want to make sure that we can go back and reference this one. But again, the goal here, as you can see, we want to hit 1, 2, 3, 4 examples, and I'm sure, as you could guess, we're going to have one of each type. Again, we're going to have an inner loop LIMACON, we're going to have excuse me, cardioid, we're going to have dimple, we're going to have convex. So again, we want to showcase, see what each of those looks like. So like I said, we've already done this first example in class, but I want to make sure that we get this thing recorded. So if we're looking at r equals 4 minus 4 cosine theta, going through, as you can see, we have more to do than just find what the sketch is going to look like. We have some other pieces of information, some other answers to find, so to speak. So as you can see, just creating a list here. We want to find the axis of symmetry. We want to find the shape. We need to find the maximum R value. We need to find the number of zeros. And we need to find the significant points. So one of the nice things that you're going to notice is being a little bit different from the rose curves is that we don't actually have to find the zeros, we just have to find the number of zeros. Another thing is that up to this point, we had not really discussed the symmetry of the LIMACON. And the reason is because it's the exact same as the rose curve. So all that we really care about is which type, meaning sine or cosine. If this were a sine problem, we would say that we're symmetric vertically to theta equals pi over 2. But since this is a cosine, our symmetry is going to be horizontal to the polar axis. So we are symmetric to the polar axis. One down, few to go. All right, so the shape, realizing, of course, that the shape is going to be dictated based on that ratio A over B. Suppose in order to determine A over B, we better know what A and B are individually. So A, in this case, is 4. B, in this case, is also 4. So when we divide A over B, that's 4 divided by 4. We get 1. All right, so anytime A over B is equal to 1, looking back at our notes here, we could see that we're talking about A over B equals 1. That's a cardioid. That's going to be our heart-shaped looking LIMACON. So A over B equals 1. That leads to a cardioid. Like this. All right. The maximum R value, the way we find the maximum R value is that we're going to find the absolute value of A plus the absolute value of B. So in this case, the absolute value of A is 4 plus the absolute value of B is also 4. So together, adding 4 plus 4 is 8. Marker down, there we go. So max R value is going to be 8. All right, so those 3 pieces of information, notice that we found those without plotting so much as a single point. Now, different when we're talking about the LIMACON as compared to the rose curves, one of the major differences is that with the LIMACON, or excuse me, with the rose curves, we had a little equation that, hey, solve this, and then you can figure out your first petal, and then it's all about the spacing from there. What we have now is a much different set of circumstances. What we have is the fact that R is equal to 4 minus 4 cosine theta. This is our equation. We need to create a t-chart where we have R and theta. The good news being that we're going to test the same 5 angular values every single time. So we're going to test what's happening when theta is 0, when theta is pi over 2, theta is pi, theta is 3 pi over 2, and when theta is 2 pi. So if you're staying with us on this, those are the 5 most obvious and simple values from the unit circle. So keeping that in mind, again, what I'm talking about, I know that it's written up here on my front board, but you can't see that here. We're talking about 0, pi over 2, pi, 3 pi over 2, back around to 2 pi. We need to know what's happening in each of these locations. So, understanding at 0, my coordinate is 1, 0. Here we're 0, 1. Here we're negative 1, 0, 0, negative 1, back around to 1, 0. So, quite literally, we're going to use substitution to complete this t-chart. We're going to say that R is equal to 4 minus 4 times the cosine of theta, in this case, is 0. So we go over to the unit circle, we identify, all right, at 0, what is the cosine? Cosine is our x term, so the cosine of 0 is equivalent to 1. So R is equal to 4 minus 4 times Cosine of 0 is 1. This cleans up to be 4 minus 4, which is 0. All of that work to determine that when theta is 0, r is 0. So now we can go up and plot this point. Remember that when theta equals 0, we're talking about this line right here. Now, apparently I erased it inadvertently, but with the max R value of 8, we're going to go off this line. So that's why in class we did it this way, to where basically each of these circles was going to be equivalent to 2. And I had these up there and must have accidentally erased. Sorry about that. All right, so back to this though. We're saying that on the polar axis, we know that r is equal to 0. If we would have gotten on the polar axis that r was equal to 6, then yeah, I'd plot the point right there. But that isn't the case. That isn't what we were given. We were told that on the polar axis, r equals 0. So we have our first significant point. So like I joked in class, this was so much fun, we can do it 4 more times, right? So we just figured out what happens when theta is 0. Now we want to get to work and figure out what happens when theta, looks like up next, when theta is going to be equivalent to pi over 2. So now when we plug pi over 2 in place, same way of playing this out, we're going to do 4 minus 4 times with the cosine of pi over 2. As we look over, in this case, pi over 2, cosine is 0. So r equals 4 minus, well, 4 times 0 is 0. R is now 4. So when theta is equal to pi over 2, I don't know why I wrote a 0. When theta is equal to pi over 2, r is equal to 4. So on my graph, I go to the angular line of pi over 2, and I count up 4 units. And there's my next point. Again, we're having the time of our lives. Let's just keep on going here. Next up, we're going to test to see what happens when my theta value is pi. So at this point, when we evaluate, r is equal to 4 minus 4 times. Well, the cosine of theta, cosine of pi, is going to be -1. And now we have r is equal to -4 times -1 is +4. R is equal to 4 plus 4, which is 8. So when theta is pi, r equals 8. So going up to my graph, we go to the angular line of pi. We count out 2, 4, 6, 8. Another one to go here. This time we're going to test for when theta is equal to 3 pi over 2. So r is equal still to 4 minus 4 times. Cosine of 3 pi over 2, as we can see again, is 0. So very similar to before, 4 minus 0, r is going to equal 4. So when theta is 3 pi over 2, r is equal to 4. So find the angular line of 3 pi over 2, and I count down 1, 2, 3, 4. We have our point. And then finally, we need to test, just to ensure that we come around full circle, we need to test what's happening when theta is equal to, that's disappointing, when theta is equal to 2 pi. And we're going to determine 4 minus 4 times with the cosine of 2 pi. Coming back around is going to still be 1. And we're going to look at this as 4 minus 0, or excuse me, 4 minus 4, which is 0, just as we were expecting. So once again, we claimed at the beginning of this problem that we should be symmetric to the x-axis. We could have used that knowledge, I suppose, to speed up the process a little bit. Okay, we also claimed that this was going to be a cardioid. So we need to draw this in a way such that it doesn't look like it's anything other than a cardioid. So we need to exaggerate, make this look a little more heart-shaped, I suppose. Also, this being a cosine problem, we're fully expecting that this is horizontal. With it being a cosine subtraction problem, we should expect that this is pointing to the left. So also needing to remember that just like with the rose curves, if we have a cosine, we need to start counting from the point that's on the polar axis. It just so happens that this particular time, kind of a special case, but the point that's on the polar axis is on the pole. So remember, I'm counting how many times we touch the pole because I'm also counting for how many zeros we should expect. So if I'm starting here on the pole, that's 1 and 2. So we have 2 zeros because we've touched the polar axis 2 times. again, like we said before, one of the nice things is that we don't have to worry about finding those zeros. We just had to identify how many to expect. So I think we are in a spot where I can get rid of this because we're ready for the significant points. Now the good news is the significant points, we've already done this. We've already found the significant points, and they are these values right here. All that we need to do is to rewrite these to where they look like coordinates. So we are at 0, 0. We're at 4 comma pi over 2. We are at 8 pi. We are at 4 comma 3 pi over 2. And then finally we're at 0, 2 pi. Yes, we do need all 5 of these to be complete. All right, so that's the way that we're going to go ahead and, like I said, and work through these. Next up, we're going to, again, start in with example number 2 tomorrow. Like I said, I wanted to make sure that we had this first one in our back pocket.